Swayam Prabha. Digital India. Educated India.
A logical and systematic approach to solving organic chemistry problems for CSIR-NET. In the module 18, we will be looking at concepts in the organic synthesis, mainly protecting groups. I am Professor Balaji, currently working at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD. Now, Ministry of Education. What we will learn? Many industrial process, drug development and total synthesis requires selective manipulation of one functionality in the presence of another competing site. So this is the major challenge, and protection and deprotection is a strategy that is being elegantly employed to circumvent this problem. Like, when there are two competing sites, we want a selective reaction at one site. So what we have to do is we have to protect the other site so that the site of interest undergoes the reaction. So this is what is the protection deprotection strategy's importance. So even though this is a better strategy, there are quite a bit of limitations, like this increases the number of steps because we have to protect one site and then we have to deprotect it. So that means literally we are increasing the number of steps, and this also leads to lots of waste generation, and it increases the cost of production when we talk about many of the industrial process. And finally, if we talk about the total synthesis, it actually leads to reduction in the overall yield. So these are some of the limitations, but although there are limitations do exist, people prefer the protection deprotection strategy in many of the synthesis methods. So let us start with the first problem. This problem was asked in June 2011. So the major product formed in the reaction of glucose with benzaldehyde and PTSA is, there are four products given here. We have to identify which is the right product. A, B, C and D are the four products that is given. And if you look at carefully in all the cases, the benzaldehyde is actually protected like this acetal. So that is what is actually happening in all the cases. So in one case, only one of the two hydroxyl groups are protected. In another case, two hydroxyls are protected by benzaldehyde, and in third one we have only one, and in the fourth one also we have only one. But the only difference is there are different hydroxyl groups that were protected in all the cases. So let us look at how the reaction actually will proceed. So we have a primary alcohol. Of course, you know primary alcohols are much more reactive compared to secondary alcohol. So when we use benzaldehyde for this particular reaction, this undergoes acetal formation with the loss of water molecule. So water molecule is lost during this protection process that leads to the acetal formation. And if we can remove the water molecule, then we can actually shift the equilibrium towards the product. So this is how the reaction actually proceeds. And when we protect it, the main thing is the primary hydroxyl is the one that undergoes the reaction first, then followed by the nearby or the neighboring hydroxyl group. So we end up with the acetal that is formed here, and we know the penyl group is a bulky group, so it doesn't occupy the axial position, whereas it occupies only the equatorial position in the final product. So this is how this simple reaction is actually carried out. So the glucose can be easily protected as the acetal using benzaldehyde. So we move on to the next problem. So in this problem, this question was again asked in June 2011. So the major product formed in the reaction of S1,2,4-butane triol with 3-pentanone in the presence of catalytic amount of PTSA is, there are four products given. And if you look at product A and B, they are 6-membered ring product, and C and D are 5-membered ring product. So this is the major difference between these two, and we have to only see there is a difference stereochemistry involved in both the products. In A and B, there is one hydroxyl group where the stereochemistry is inverted between the two products, and similarly in C and D, one of the hydroxyl which is protected as the acetal is actually inverted in this case also. So the protection is basically acetonide protection. So let us look at how the reaction actually proceeds. So we have 1,2-diol in the compound. Similarly, we have 1,3-triol also is present in the compound. So now the competition is between the protection of the 1,2-diol versus 1,3-diol. So they both can actually react with the carbonyl compound. So when both any one of them reacts with the carbonyl compound, so here it is nothing but the ketone that is used in this particular case. So if the 1,2-hydroxyl dihydroxyls undergoes protection, then we end up with a 5-membered ring product as shown here. And if it is a 1,3-diol, if that is getting protected, we will end up with a 6-membered ring. So now we have to figure it out whether it is a 5-membered ring product or a 6-membered ring product. If we draw the 6-membered ring in the cyclohexane chair conformation, then we will actually find it out. There is a 1,3-diaxial interaction that is happening in this particular system. So we have two 1,3-diaxial interactions that is happening, which is quite unstable. So due to that reason, this reaction does not, that means the 1,3-diol protection does not proceed further, and we only end up with the 1,2-diol protection. And in both the cases, the primary hydroxyl is the one which undergoes as one of the hydroxyl, and there is the second hydroxyl. And that's how we can easily figure it out, like which compound will be actually protected in this particular case. And the final product is actually the 5-membered one. The reason why we get the 5-membered one is to avoid the 1,3-diaxial interaction if the 6-membered ring product is actually formed. Let us move on to the next problem. So this question was asked in December 2011. So the reaction given below proceeds through, there are compound, some intermediate A and the product B are given, and benzaldehyde is actually treated with the Wittig reagents in the presence, followed by reaction with the lithium aluminum hydride at -78 degree. That leads to one intermediate A. This is treated with 3,4-dihydropyran in the presence of PTSA. So this will simply protect the hydroxyl group. So this is the overall reaction, and we are now going to find it out what is the intermediate A and what is the final product B. So if we look very carefully, the reaction of the benzaldehyde with Wittig reagent will give a alpha beta unsaturated ester. So that is the step number 1. And in the step number 2, that ester is treated with the lithium aluminum hydride. So when we treat an ester with the lithium alpha beta unsaturated ester with the lithium aluminum hydride, that will reduce that ester group and we end up with the allyl alcohol. So this is the overall reaction that will happen. So that means the compound A is actually going to be an allyl alcohol. And if you look at the combination of 1, 2, 3 and 4, where A and B are the one of the intermediate, B is the final product. So 1 has the allylic alcohol unit, 2 also has the allylic alcohol unit, 4 also has the allylic alcohol unit. So 1, 3, 4 are more probably the intermediate. A 3 is not the one, because 3 both the double bond and the ester groups are reduced. So that's not the product. So we can easily say any one of them will be the product. And now we have to only see what is going to be the final product, that is the tetrahydropyranyl ether. What is that product we are going to see? And if you look at 1 and 2 and 4, the oxygen groups are little bit far away in 2 and 4. In 1, the oxygens are in the adjacent carbon. So we will have to see which is actually going to be the right product. So based on that, we can actually find out which is the right substituent. So the first reaction is the Wittig reaction. So that leads with the E selectivity. So we end up with the alpha beta unsaturated ester. And this alpha beta unsaturated ester on reduction with the lithium aluminum hydride gives only the E selective alcohol, that is the allylic alcohol. And if we go back to the starting material, the first question, so 1 is having actually the cis isomer, and 2 is also having the cis isomer. That means 1 and 2 may not be the right one, and obviously we can easily figure it out. It is going to be the C that is going to be the 4 is the one that is going to be our final product. So once the allyl alcohol is formed, the allyl alcohol is now treated with the 3,4-dihydropyran in the presence of an acid, that is a paratoluene sulfonic acid. This undergoes the protection of the alcohol unit by this dihydropyran, and the resulting product is a 2-tetrahydropyranyl ether. So in this case, the oxygen or in the adjacent the same carbon we have both the oxygen unit, and if you are looking at proton NMR to find out, we have a specific hydrogen which appear around 4.5 or close to 5 ppm. That clearly tells, like, I mean, this tetrahydropyranyl ether is actually formed in this reaction. So that way we can also spectroscopically confirm that what is the product that is formed, and this way we can easily find out how the benzaldehyde is getting converted to a allyl alcohol, followed by protection leads to the tetrahydropyranyl ether. And let us move on to the next problem. So this question was asked in June 2011. So a suitable catalyst for bringing out the transformation given below is, we have a carbonyl compound, that is cyclohexanone. This is treated with ethane dithiol, and we end up with a carbonyl protected group. 1,3-dithiene is the product that is actually formed in this reaction. So here if you look at there is a water molecule that is lost in this reaction. So this is one hint or clue which is actually given in this reaction. So based on that, we have to find it out what is the reagent that will be used. So 4 different reagents are given. One is BF3 ethyrate, the second one is sodium ethoxide, the third one is tungsten lamp, and the fourth one is dibenzyl peroxide. Before we work out what is the actual reagent, let us look at what are the individual reagents and what they will do, that we will see. The first one is a BF3 ethyrate. BF3 ethyrate is nothing but a Lewis acid. So the Lewis acid is generally used in reactions like Friedel-Crafts acylation reaction, Friedel-Crafts acylation and alkylation reactions, Mukiyama aldol condensation, like various reaction, and the carbonyl addition reaction. Many reactions use Lewis acid as a catalyst in their reaction. So this is reagent number 1. And the next reagent is sodium ethoxide. So sodium ethoxide is a strong base. So whenever we use a strong base, what will happen is an carbonyl compound can generate the carbanion from this particular reagent. So that carbanion can be stabilized by the enolate anion as enolate anion. So they can undergo reactions which are similar to aldol, or similar condensation reactions are possible. So if you use a base, then obviously this reaction may lead to a condensation product and not the protected product. And if we go to the next one, which is a tungsten lamp is nothing but a heat source. So heat source means generally in many of the halogenation reactions this is used, but here we do not have any halogen, so we can assume that this may not be the right reagent. And the last one is dibenzyl peroxide. Dibenzyl peroxide is nothing but a radical initiator. So if this cyclohexanone or maybe 1,2 ethane dithiol, if any of them undergoes a reaction, then they will preferably undergo a radical reaction. So that is the only thing, and here we do not see any radical reaction. So that is the reason dibenzyl peroxide is also not the reagent that can be used for this reagent. So if you rule out what are all the reagents which cannot be used, base cannot be used because that will lead to aldol condensation, and the heat source is not the one which is required because in this case we do not have any halogenation or similar reactions. A radical initiator is also not present because we do not have any radical reaction in this case. So what is left out is only the Lewis acid, and we already know Lewis acid can actually coordinate with this carbonyl oxygen. So that is the reason this reaction can easily be facilitated using this one. And basically once it is coordinated, then we have a delta plus charge on this carbon. So sulfur has a lone pair of electrons, so that can come and attack here, and that is how we can actually initiate this particular reaction. So in other words, this reaction can be initiated by the presence of Lewis acid. So the reagent that is used for this reaction is nothing but a Lewis acid. And of course, when we look at the cyclization, so what will happen is once the thiol is added to this one, so the sulfur will form the first carbon bond, carbon sulfur bond will be formed first, and then with the loss of the hydroxy unit, the second sulfur will be attached to this one. So that way what we can actually see is the cyclization leading to 1,3-dithiene formation can be easily visualized. And since water is removed in this particular reaction, generally we can use Dean-Stark or similar water removal mechanism so that this reaction proceeds to completion. So let us move on to the next problem. So this is also asked in June 2011. A suitable reagent combination for carrying out the following transformation is, we have a diol. So cis diol is given here, and this is actually protected as a acetonide, and we are going to see what is the right reagent that will be used for this particular reaction. So 4 combinations are given. The first one is trimethyl orthoformate with PTSA, that is acid, that is the second one is trimethyl orthoformate with the sodium hydroxide, which is a base, and the third one is 2-methoxypropene and PTSA, so that is again an acid. The last one is 2-methoxypropene and sodium hydroxide, so this is nothing but the base. So we have 2 combinations where 2 reagents are treated in the presence of an acid or base to give the protected product. So now we will have to find it out, like, what could be the reagent that will be used in this reaction. And if we carefully look at the reagents that are used in this reaction, the first one is trimethyl orthoformate. Trimethyl orthoformate is generally used for the, this is nothing but an orthoester. This is used for the protection of aldehydes as a acetyl group. So trimethyl acetyl only can protect an aldehyde, not a carbonyl ketone also. It's only protects the aldehyde. But we have here 2 hydroxy units. So that means we can easily rule out it cannot be the first reagent. Trimethyl orthoformate is not the reagent for this particular transformation. So that leaves with, we have only 2 choices to look into, which is the 2-methoxypropane. One is under acidic condition, another one is under basic condition. So we will have to now see what is the most appropriate one. If we are actually going to use basic condition, the basic condition will actually generate an anion. So this is one of the problem. And we have a alkene. So alkene is again electron rich. So we have 2 systems. One is electron rich alkene, the another one is a anion in the presence of base. So both will repel each other. In other words, a base cannot be used to initiate any of this reaction. So that is completely ruled out. Then what is the other thing which is left out? We have the acid. So what acid can do? Acid can actually protonate this particular alkene double bond. So if the alkene is protonated by the H plus ion, then that will create actually a delta plus charge in one of the carbon, and that can easily be attacked by the hydroxy unit. So that is how the reaction actually can go step by step. So we can clearly say this reaction can only be initiated in the presence of an acid. In other words, the reagent for this particular transformation, that is the diol protection as the acetonide, is nothing but 2-methoxypropene in the presence of PTSA, that is the acid catalyst. Here, methanol is the byproduct that is formed in this reaction. So let us move on to the next problem. This was asked in June 2016. So the major product formed in the following reaction, we have a couple of protecting groups. One is a OBN, benzyl protection. CBC is another group, and we have BOC. So we have 3 different protecting groups that are involved, present in the starting material. This is treated with the hydrogen and 10% pelletized carbon in ethanol as a solvent. So now we have to know what is the reagent that will do and what are the group that will be actually deprotected. So we have 4 combinations, A, B and C and D are the 4 different product that will be formed. So if you look at all the reagents, in the first one, the benzyl group is actually deprotected. We end up with a corresponding carboxylic acid, and CBC also is removed to get the amine, whereas the Bach did not undergo any change. So this is product number 1. And in the second one, all the three groups are deprotected by the hydrogen and the palletized carbon. In the C, the carboxylic acid is deprotected. Both the nitrogen groups are not deprotected. So this is the third product. And the last one, only the amino group is deprotected and not the aniline is deprotected. So these are all the 4 different combinations, and only thing what we have to know is what is the role of hydrogen and 10% palletized carbon. So this hydrogen and 10% palletized carbon deprotects both ROBN, that is benzyl group, benzyl ether basically, and here it is the benzyl ester will be there, and CBC are the 2 groups that are deprotected by the use of palletized carbon. So in other words, the compound A is the only product where the N-Bach did not undergo deprotection in the presence of hydrogen and palletized carbon. So that is the product that will be formed in this particular reaction. Let us move on to the next problem. So here the kinetic product formed in the following reaction. We have a compound starting between an amino alcohol is actually given, and we have to find it out what is the reaction this amino alcohol will undergo. We have 3 different reagents that are given. One is the Bach anhydride in the presence of pyridine, that is the reaction number 1. The second one, TBS chloride or TBDMS chloride, tetrabutyl dimethyl silyl chloride in the presence of imidazole. And the third one is lithium aluminium hydride, tertiary butoxyhydride. So this is a reducing agent in the presence of ethanol and minus 78 degrees centigrade. So there are 3 different reaction conditions given. The Bach anhydride is generally used for the protection of amino groups. So this is one hint we can easily get from this reaction. The second one is TBSCl or the TBDMSCl imidazole combination is generally used for the protection of hydroxyl group, and the reducing agent lithium. See, this is not lithium aluminium hydride. Lithium aluminium hydride is a very strong reducing agent because this is a tertiary butoxyhydride. So this is a milder reducing agent compared to the lithium aluminium hydride. So this may reduce a carbonyl group. So these are all the tentative things we can actually assume. So based on that assumption, if we work it out, what is the product, if we have to see is A, B and C, D are given here. So the Bach anhydride will protect amino group as a Bach. Okay. Then the TBDS will protect this hydroxy unit, and the alcohol will be reduced, this ketone will be reduced to alcohol. So these are all the 3 things, and let us look at what are all the product that has this combination. So A has OTBS, NH-Bach and the hydroxyl. So A may be one of the product that we can assume. And if we go to B, the oxygen, the hydroxyl is also protected as the Bach group, but generally Bach anhydride does not protect that alcohol. So this is ruled out. This may not be the product. But if we come to C, the amino group is protected as Bach, so that is possible, and the hydroxy is protected as TBS, that is also possible. The carbonyl is reduced, that is also happening, but the only difference is the stereochemistry of A and C are opposite to each other. That means these 2 are enantiomers. Now let us move on to the last one. The last one is similar to B, so we can easily say like the hydroxy group is not protected as Bach, so D is also ruled out. So now only thing we have to find it out is whether it is A or C. That is the only thing we have to find it out. So if you look at the individual reaction, the first step is the protection of the amino group using the Bach anhydride, that leads to N-Bach protection. And the second thing is a reaction with the TBSCl that protects the hydroxy unit. So that is also, as we have discussed earlier. So that is also happening. So what is the only thing that is happening we have not confirmed is the reduction of the carbonyl group. So here we have the hydroxy group that is away from the observer. Now this is a little bit complicated one to understand, and we have to now use certain models to find it out. Exactly, the model what we are going to use is basically the Zimmermann-Trexler model to find it out how this reduction actually takes place. So here we have a aluminum tertiary butoxy hydride, which is a pretty bulky reagent. So since it is a bulky reagent, the hydride transfer takes place from the less hindered site. So we can draw the molecule as shown here, and like Newman projection, we can draw the structure. And here the hydride ion comes and attacks the carbonyl from the place, from the least hindered site, that is from the close to the hydrogen which is present. So that leads to the hydroxy group going away from that. So when we redraw the same structure, we can actually see the hydroxy group is actually away from the observer, and this is how we can easily find it out how the final product stereochemistry is arrived at. So this way we can easily tell the overall reaction, the product is going to be the hydroxyl, where it is actually pointing away from the observer is the final product. Let us move on to the next problem. So this question was asked in December 2013. The major product formed in the following reaction sequences. So here we have a polyhydric alcohol, and this is treated with benzaldehyde in the presence of PTSA, followed by reaction with the sodium periodate and then sodium borohydride reduction. So these two things are happening simultaneously. So four different products are given: A, B, C, and D. Now A is one compound where the benzaldehyde is actually used as a protection of two hydroxy units, and the ring structure is actually broken to end up give the primary and the secondary alcohol. So this is one product. And in the another case, what happens is, like, again the benzaldehyde is used for the protection of two hydroxyl unit, and the rest of the molecule is actually opened up because sodium periodate actually opens the diols. So 1,2-diols can easily be cleaved by sodium periodate. So we have plenty of diols. So we have one part here, another one here, another one here. So we have three different 1,2-diols are present. All of them can be actually hydrolyzed, or broken by sodium periodate. So that means we may end up with multiple type of products. So in one of the product, 2-hydroxyl, any 2-hydroxyl, we'll have to see which two are the hydroxyl that were protected using this benzaldehyde. Then the rest of the molecule is actually opened up. So B and C, if you look at, both of them have the benzaldehyde protecting 2 hydroxy units, and the rest of the molecule is actually opened up. And if we look at the product D also, this also has the same way. So if we look at what are all the different hydroxyl that are protected, so we may look at these two as one combination, these two as another combination, these two as another combination, these two as another combination. In other words, there are 4 2-hydroxy units are there, and all the 4 2-hydroxy units can be protected as a benzaldehyde unit, as an acetal, and all the 4 products are actually given. Now we will have to work it out each one separately to find out how the things will go. And if we look at the starting material, we can easily figure it out. It has one primary hydroxyl, and the rest of the hydroxyls are actually secondary hydroxyl. So we have seen this earlier also. Whenever we have a primary hydroxyl which is more reactive compared to the secondary hydroxyl, then reaction with benzaldehyde generally reacts with the primary hydroxyl as the most preferred one. So in other words, what we can say is the primary hydroxyl is easily protected with the neighboring hydroxyl as the acetal unit. So this is what actually happens, and this is a very crucial thing. So once we know, then we can easily figure it out. The other three combinations are not going to work because these two hydroxyls are not protected, because these two are secondary hydroxyls. These two are also not protected, so that means they are also again secondary hydroxyl, and similarly these two are also not protected. In other words, without looking at what is the actual product, we can easily figure it out what is going to be the one. So if we go back to our starting material, the four combinations, A is actually going to be the product. Without even looking at what are the other combinations, we can easily say that because A is the only compound where the primary hydroxyl is actually protected as the acetal, not the rest of the things. So this way you can also sometimes guess what is going to be the product. And finally, we can also work out the reaction to find out what is the actual product that will be obtained. So here the only thing is which hydroxyl, and of course we do not have multiple products given, and we only have one product where the primary hydroxyl is protected. So we can clearly assume that this is going to be the product. So reaction of this diol, this is actually the triol we have, and this reaction with sodium periodate and sodium borohydride cleaves this compound into a hydroxy derivative, carbonyl derivative, and that carbonyl derivative, that is the aldehyde, which undergoes reduction in the presence of sodium borohydride to give this particular final product. So this way we can easily say what is the final product that will be obtained in this particular set of or sequence of reactions.